Alright, this is our 5.08 lesson over rectangles, kites, and trapezoids. First, we have our rectangle. Now, a rectangle has several properties that we can see here. Many of the properties are properties of parallelograms. So, for example, if you read the first 5 bullet points that we have here, those are all representative of properties that a rhombus and a square have as well. However, if you look at the last 2, those are unique to the rectangle. Alright. Now a square has these also. So just keep in mind that the properties the square has are the properties of both a rhombus and a rectangle. And so what we're going to do is we're going to explore some examples using these properties. So I would refer to this as a reference sheet or a slide for the properties when we refer back to problems that involve rectangles particularly. Let's go ahead and take a look at these 2 examples here. So if you look at the example on the left, we have a rectangle where the angles that they're referencing are this angle here and this angle here, angle BAC and CAD. So notice how both of the angles together make up the right angle. Because of that, we know that the sum of the 2 angles is equal to 90 degrees. So they can go ahead and substitute the expressions in for those angle measures, as they've done in blue and red, and then they combined like terms. So the 3x and 2x becomes 5x. Then they're subtracting 10 on both sides and dividing by 5 to get 16. So this is an example of what we could do in order to kind of use that property that rectangles have right angles to solve an actual equation and find the value of x. So this is an example of rectangle problem that you might encounter. Here's another quadrilateral that's a rectangle, and it's utilizing a property that rectangles also possess, which is that we know that the diagonals here are going to be congruent, and they give us AC as well as DE, right? So AC is the 5x minus 1, and DE is the 2x plus 3. Now, DE is only half of a diagonal, so what we can do is we can double the length of DE by multiplying it by 2, and that should equal the length of the full diagonal AC. So we can see right here that they've substituted the expression for DE in, and we're distributing 2 to both of the terms. So we have 4x plus 6 equal to 5x minus 1. Then they're subtracting 4x on both sides, so they get the x isolated, and then they add 1 to both sides, and voila, we have 7 as our value. So, as far as rectangular examples are concerned, these are 2 really great examples that you can refer back to when you're trying to figure out how to solve an equation or set up an equation. And both examples demonstrate 2 separate properties that rectangles actually possess. We get to the kite now. The kite is a quadrilateral with 2 sets of adjacent congruent sides. We can see that those sides are represented here as well as here. Now, having said that, it is also a quadrilateral, and it is not a parallelogram, unlike the previous 3 figures that we've discussed. So it is still a part of the family of quadrilaterals, and we can go ahead and take a look at a few applications of that. Before we get to that, we want to look at all of the properties of a kite. So, as I mentioned, we have 2 sets of adjacent sides that are congruent, so these sides as well as these sides. And we also recognize that we have a pair of opposite angles that are congruent. So you can see that's highlighted here in blue, here and here. Now it's only those opposite angles that are congruent to each other. So one little point of interest here that I'm going to make is that one of the diagonals, or one diagonal, bisects the other. So what I mean by that is this diagonal represented in the highlighting of red here is bisecting this diagonal here. That means it's cutting it in half, right? Because bisection means to cut into equal halves. It's also, as you can see, perpendicular, so the diagonals are indeed perpendicular. I would also add a few things as well to this. You can actually see that the diagonal highlighted in red, if you want to refer to that as AC, that's perfectly fine. AC is a perpendicular bisector because it's perpendicular to the segment it's bisecting, but also it's an angle bisector. You can see that if you look at the angle at the top, which is located at the vertex A, as well as C, it is bisecting the entire angle there, which was 98 degrees. And down here, that would have been 54 degrees, but it's bisecting it into two congruent halves. And so that is also a fact of kites as well. So this diagram is a great diagram to refer to because it kind of shows all the different properties that a kite possesses. So let's go ahead and take a look at some practice problems. So here we have a kite and we want to determine the following. We want to determine which statement is correct or accurate. So here they're actually telling us is the measure of angle CDE, which is this angle, congruent to the measure of angle EDA, which means that their measures are equal, like they're saying. Well, in this case, that would imply that this entire diagonal is an angle bisector, if that's true. And that's not true, okay? This is not the angle bisector. The only one that's an angle bisector is this one. So those two angles are not going to be congruent. That is not the case here. You can also justify it because in this case you have right triangles on the top where they share a side, which is like a leg, if you will. We also know that this half equals that half, and we know that these are congruent to each other as well. Those triangles are the triangles that are congruent to each other. Okay. It's not going to be this triangle congruent to this triangle. It's this triangle congruent to that triangle. So that's why these angles cannot be equal in measure. The other three are actually true, and for various reasons. If you look at angle DAC, which I'll go ahead and stop highlighting those, angle DAC is this angle right here, and angle BAC is this angle. This is true because this is an angle bisector, so those are going to be two equal or congruent angles, as you can see right there. And that is true because those triangles are congruent, and so corresponding parts are congruent. Lastly, we have ADC as well. ADC is referring to this entire angle, and ABC is referring to that entire angle. Those are the opposite angles that I highlighted in blue earlier. Those are congruent to each other. The opposite angles are congruent to each other, so that is also true. And then lastly, to highlight this in kind of an orange color, the entire segment that is DB has been bisected by that vertical diagonal. So those two parts there, which are represented as ED and EB, are in fact equal. That's why those three statements are true. We can also take a look at an application of the Pythagorean theorem. So here, for example, we are looking for the length of SP, and we know that these two lengths are 8 and 6. And we recognize, by the way, that at angle T, it's a 90-degree angle. So since the diagonals are perpendicular, we have a 90-degree angle or a right angle, and we can utilize the Pythagorean theorem to figure out the missing length of SP. You can call the S length SPC if you wish, because we know Pythagorean theorem is often remembered as this. You can use that certainly to help you remember it, but just keep in mind it's leg squared plus leg squared equals hypotenuse squared. So here we have 6 squared plus 8 squared equals C squared. That's 36 plus 64, which equals C squared. So that's going to be 100 equal to C squared. And then we take the square root of that to get C, which is equal to 10. So SP is actually the length C, therefore SP is going to equal 10 as a length. So here's an example of where we found this length of a kite, and it was a missing length, and we're using our knowledge of Pythagorean theorem and the knowledge of the diagonals being perpendicular, right? Because remember, the diagonals in a kite are perpendicular. So diagonals are perpendicular indicates that we can use right triangles and rules and theorems related to right triangles to help us solve problems like this one. Okay, let's take a look at the trapezoid. So a trapezoid is a quadrilateral that has two sides that are legs. So we have a leg here and a leg there. We have two sides that are bases, so here, and we have one set of parallel sides as well. So you see the parallel symbols are right there, and that's what makes up a trapezoid. Now, having said that, recall that a trapezoid is going to have two pairs of base angles. So we can kind of see using pins here, we have angle B and C, and we have angle A and D. Those are base angles to each other, of course. And with that being said, the same side interior angles are going to be supplementary from A to B and from C and D as well. So what we're referring to there is that since these are parallel bases, these are called same side interior angles, as are these. That just means that they're going to be supplementary to each other, and so they add up to 180 degrees. Notice how these are not same side interior to parallel lines. They're non-parallel lines that we have because these are the legs and they're not parallel. So these are not supplementary to each other. They're same side interior angles for certain, but they're not supplementary in this case because those green lines I highlighted are not parallel to each other. So let's take a look at an application utilizing what we call the mid-segment theorem for a trapezoid, or you can think of this as just the mid-segment rule if you wish, okay? So the mid-segment rule that we have is the average of the two bases that will be the length of the mid-segment. So another way of saying that is the mid-segment of a trapezoid is half the sum of the measures of the bases, and we also recognize that the mid-segment is parallel to the bases. So this segment is the mid-segment, and it is parallel to these bases here. And we can go ahead and plug in our mid-segment length, which is actually given to us. It's 10. And we can go ahead and combine these together. So we have x plus 2 plus x plus 12. And we're going to divide that by 2. Now, we can combine like terms, so recognize that we have x, and we have 2 and 12. And so that's going to get us 10 is equal to 2x plus 14 divided by 2. Then I can go ahead and multiply both sides by 2 if I want. It's not the only thing I could do here, but it's probably the more formal approach. So I'm going to go ahead and do that. And we get 20, and we get 2x plus 14. Now I can subtract 14 on both sides. So that allows me to say 6 equals 2x. And if 6 equals 2x, we can divide both sides by 2. And so now I get 3 is equal to x. So x is going to equal 3 in this case. So that's an example of applying the mid-segment rule that we have there as well. You can also see an example here where you're looking for the mid-segment length, but you'll notice that it's the thing that's actually missing. So the mid-segment is x, and we're just taking the average of 12 and 24, which is a numerical approach really, so it's just 36 divided by 2, which is 18, right? So there's a case where you might be missing the mid-segment, and then there's a case where you might be given the mid-segment and you're missing a variable. In the final problem, or the final type of figure, we're looking at a trapezoid still, but this time it's an isosceles trapezoid. So just like an isosceles triangle, the legs of the isosceles trapezoid are congruent, so we know that these are actually congruent to each other. And an isosceles trapezoid has the following characteristics. Each pair of base angles are congruent, so angle B and C, as well as angle A and D. They are congruent to each other. We also know that the diagonals of the trapezoid that are isosceles are congruent, so these lengths are also congruent to each other as well. And so that is another feature that we can pay attention to. So there's really kind of 3 that I want to kind of single out here a little bit. So you've got the legs are congruent, the base angles are congruent, and the diagonals of a trapezoid are congruent. That being the case, if you want to prove that it's an isosceles trapezoid, you have to show that or prove that one pair of base angles are actually congruent. You have to prove that the diagonals are congruent, or you have to show the legs are congruent. Okay, so if you can show one of those 3 things, you can verify that it's an isosceles trapezoid. Okay, so with that being said, I'm going to go ahead and take a look at that diagram and kind of demonstrate like how I would go about doing that. So if I have an isosceles trapezoid here, then what I could do with the isosceles trapezoid is I could first determine the slopes of the 2 lines that I have that are bases, right? So BC's slope, or let's use MBC for slope, right? We can see that the slope is going to be 0 because it's a horizontal line. That means it has no incline. And the slope of AD is also going to be 0 because it also has no incline whatsoever. So what does that imply? Well, it implies that BC is parallel to MD. Or I guess should say AD, isn't it? Yeah, AD. So that tells me that it's a trapezoid, at least so far, as to show that the other segments, AB and CD, if you look at their slopes, their rise, it goes up by 4, and then it goes over by 3. And then this one goes down by 4, and it goes over by 3. So what does that tell me? Well, it tells me that the slope of AB is a positive 4 over 3, and the slope of CD is negative 4 over 3. And it should be plus 3, by the way. I apologize for that, because it goes to the right by 3. So that tells me that because those are not equal to each other, that AB is in fact not parallel to CD. So we have only one pair of parallel sides, so that means it's a trapezoid. And then to verify that it actually is a isosceles trapezoid, you can use the distance formula if you want. But also notice how when I did rise over run, I created these lovable little right triangles. And those right triangles actually have leg lengths, right? So you've got 4 and 3, and the other one, even though it's negative 4, if you think of it as going down, the length of it is still 4, and it's still 3. So we can see logically that using Pythagorean theorem, we can confirm that the lengths of these legs are both going to be 5. So that tells me that BA, the length of BA is actually the same as CD. They are going to be the same. So if you have congruent legs, that means this implies that it's an isosceles. It's an isosceles trapezoid. We proved that it's a trapezoid in the work above in blue and red, and then the work below kind of confirms that those leg lengths have to be the same because they both would possess the same hypotenuse length, and therefore it would have to be an isosceles trapezoid. That certainly is one way that you could verify it. Okay, so with that being said, you could look at this problem on your own and check on Desmos calculator to see if you can confirm that in fact this is also an example of an isosceles trapezoid. So please refer to the video that I've posted in our channel as well that kind of explains how to input ordered pairs like this and show a polygon or a figure in either Desmos or even GeoGebra. So looking at your exit ticket, you have to do something very similar to this in your first problem. So I encourage you to use the Desmos graphing calculator to input the points to see what it looks like, similar to my diagram that I just demonstrated. And you can confirm that it's an isosceles by showing that you have either congruent legs, or you have congruent diagonals, or you have congruent base angles as well. And the other two, I would refer you to the kite properties slide. So go to the kite properties slide. That can be very helpful here when answering these two questions. You're finding the measure of WXY, which is this angle right here. And over here, you're finding SP. Now this one, I would refer you back to one of the slides because we covered a problem just like this. So I certainly would reference that in the slides directly. And then again, in this example in the middle, I would refer back to your slides that we talked about over kite properties to help you break down the different angles. For example, they're giving you 38 degrees right there. They're telling you ZYW is 15 degrees. So how can you use your knowledge of the relationship of the diagonals of a kite to help you figure out all of the angles necessary so that you can determine this exact angle right here? That would be my challenge to you as you're going through this and thinking about that problem. And that slide would be very helpful in that. So that's going to be our lesson on 5.08 over rectangles, kites, and trapezoids.